Hello everyone, hope you're all doing well in these difficult times of the pandemic. My name is João, and I'll be presenting an article entitled Numerical Simulation of a Hybrid System of Photovoltaic Panels, Electrolyzer, and Solid Oxide Fuel Cell that was supervised by the Professor Florian Pradelle. First, it's important to remember our increasing global energy demand. This demand requires more efficient ways to energy generation with lower environmental impact, as the decarbonization process. As a solution, there's the entry of renewable sources, such as the solar energy. If you analyze the figure from a British petroleum study, we can see that from last decades to now, renewable sources increased its participation in the global energy matrix, while oil and coal, for example, decreased. It's also interesting to combine the largest participation of renewable sources with hybridization and storage systems that maximize energy efficiency and avoid the disadvantage of the intermittency. So, our main objective with this study is to develop a numerical simulation of a hybrid system with photovoltaic panels, electrolyzer, and solid oxide fuel cell. And our studied system consists in photovoltaic panels, electrolyzer, a solid oxide fuel cell, and a current inverter, as you can see in the figure, coupled in a small-scale residence for electric supply purpose. We also considered a low-temperature PM water electrolyzer, as it is more appropriate for this system. The photovoltaic panels provide a direct current that goes to a load controller that sends the required power to the residence and the eventual power surplus to the electrolyzer for hydrogen production, accordingly to the hourly electric demand. When the demand is higher than the photovoltaic power, the fuel cell consumes the hydrogen from the storage tank and oxygen from the air to produce electricity and high-temperature gases that can be also used in a heat recovery steam generation unit. The photovoltaic and fuel cell power outputs are converted in a DC-AC inverter to meet the power requirements of the house. We will also assess the technical feasibility of the system by applying the simulation under typical conditions of the district of Xerém, located in the city of Duque de Caxias, in Rio de Janeiro, Brazil. Our methodology consists in two input data, the solar irradiance and the residential electric demand. The solar irradiance from the current voltage characteristics curves defines the photovoltaic power output. When the photovoltaic output surpasses the electric demand, this power surplus goes to the electrolyzer for hydrogen production. In the electrolyzer, we use the electrolyzer efficiency equation to determine the hydrogen flow rate, since we know the energy efficiency from the literature. The hydrogen produced is then compressed and stored in a tank. Its compression consumes 0.7 kWh per kilogram of the produced gas. When the demand surpasses the photovoltaic power, the fuel cell consumes the hydrogen from the storage tank and oxygen from the air. Now, from the fuel cell, the solid oxide fuel cell equations used in the literature, this fuel cell hydrogen flow rate returns the fuel cell power output needed to meet the residential electric demand. Therefore, our study is based on the phenomenological model of photovoltaic panels and thermodynamics of fuel cells, simulated in MATLAB. Then, we applied this simulation in a case study, as I said before, in the district of Xerém, in order to evaluate the technical feasibility of the studied system. The image shows the solar irradiance in this location during typical days of summer, winter, and spring. And also, for the development of the model, we made some assumptions, as the hybrid system is always on steady state conditions. There is the consumption of 0.7 kWh per kilogram of hydrogen for gas compression for its storage, and heat losses from the system boundary are not considered, as the contact resistance in the fuel cell and possible sources of data noise. Now, for the results and discussion section, we started validating our simulation by comparing its results with the data from the literature. Husseini studied a similar hybrid system under other typical conditions which based our study. Therefore, in this comparison, it is possible to identify the qualitative similarity between the data in the graphics. Also, there is the quantitative difference, since the input data is not the same, as different photovoltaic panel characteristics, different multiplicative factors, etc. Those graphics show the evolution of the energy surplus, which is the difference between the photovoltaic power and the electric demand. And here, we make the same analysis for validation purpose. We notice the qualitative similarity, however, the quantitative difference, due to the difference between the characteristics of the photovoltaic panel. Those graphics represent the hydrogen production rate in the electrolyzer, which happens only when the photovoltaic power surpasses the electric demand, as mentioned before. Now, these are few graphics with very important data. First, there is the electric power demand of the studied residence. We can see the peak around 8 o'clock p.m. Next, there is the difference between the photovoltaic power and the demand. However, it can be seen that during winter there is no positive values. That indicates that there will be no hydrogen production during this season. And last, the last figure presents the hydrogen balance through the day. This includes the amount of hydrogen produced, stored, and consumed by the fuel cell. It is assumed that there is an initial hydrogen storage so that there are no negative values. During summer, the final balance of hydrogen reaches 1.2 kilograms, indicating the very high feasibility of the proposed configuration. During spring, the final balance is very close of the initial amount, indicating a slow consumption of the stored hydrogen. And finally, in winter, there will be a total consumption of the fuel initially stored. However, under real conditions, the electricity demand should be provided by the grid. Next, we will study the solid oxide fuel cell operation and how its configuration can influence the results. There are two important parameters that define the fuel consumption in the solid oxide fuel cell. They are the recirculation ratio and the fuel utilization ratio. The recirculation ratio indicates the percentage of fuel that exits the fuel cell, which will return to the fuel channel entry, mixed with other gases. This is interesting due to the reuse of fuel. Both parameters, the recirculation ratio and the fuel utilization ratio, may vary in order to reach higher efficiency. Therefore, the figure presents the energy and exit efficiency of the solid oxide fuel cell during summer, winter, and spring, varying the parameters. First, we'll study the fuel utilization ratio variation, while the recirculation ratio is fixed in 20%. A higher fuel utilization ratio returns higher efficiency, as we can see in the yellow line. Another observation is the solid oxide fuel cell operation during winter. We can see that during summer and spring, the efficiencies drop. In fact, they are null during the day, since the photovoltaic panels fully provide the energy load, and the fuel cell is now shut down. During winter, the photovoltaic panels does not produce enough power to supply the demand. Then it is required the solid oxide fuel cell operation during this period of the day. That explains that the fuel cell was not shut down during winter. Therefore, with a fuel utilization ratio of 85% and recirculation ratio of 20%, it reached a maximum energy efficiency of 93.37% and exit efficiency of 93.02%. However, with a fuel utilization ratio of 65%, the maximum energy and exit efficiencies are 75.19% and 74.91% respectively. Now, a similar analysis is made, but fixing the fuel utilization ratio in 85% and assessing the variation of the recirculation ratio. With a recirculation ratio of 30% and a fuel utilization ratio of 85%, the maximum energy and exit efficiencies are 94.38% and 94.03% respectively. Those are the highest efficiencies reached in this analysis. However, with a recirculation ratio of 10%, the maximum energy and exit efficiencies are 92.34% and 91.99% respectively, which is still a high value. And this analysis concludes that the higher these parameters, the recirculation ratio and the fuel utilization ratio, higher energy and exit efficiencies are reached. For conclusion, we can see that in Xerém, Duque de Caxias, it's produced 1.062 kilograms of hydrogen per day during summer, 0.32 kilograms of hydrogen per day during spring, and no hydrogen during winter. The maximum energy and exergy efficiencies reached are 20.9% and 22.4% for the photovoltaic system, 94.38% and 94.03% for the solid oxide fuel cell operation, and 30.5% and 32.25% for the whole hybrid system. Therefore, during the winter, the studied system is not technically feasible, different from the operation during the summer and spring. For future work, an economic feasibility analysis is considered, as it should be the critical point to enable the hybrid system installation, and also the simulation of more days of system operation. Thank you very much for the attention, and for any questions, I'm available.